So in this video we want to look at a linear map T from Rn to Rm, and we want to show that first of all that it is differentiable, and then we want to calculate its derivative. And so we kind of guessed what it was, and so we want to kind of confirm that our definition of the derivative does actually, give us things that make sense. So let's have a look. We want, let's start off by showing that there indeed is a linear map for which this remainder function, this r of, so in this case, so we want to show it's differentiable, basically any Rn, so we just want to pick some, let x be an element of Rn, okay, and we choose the linear map, we choose it to be T, okay, we let d of x, we just, okay, fine, so over here, I think there was a slight mistake from what I said before, okay, so we actually don't know that the derivative exists yet, so we just need it to be some function, some linear function. Let's call it t. I like calling linear functions t. Okay, this is not Gecko. And then if it exists, if this function it has this property that it's very small, then the derivative of x is equal to t. Okay, so it was just me messing up. It was just me doing things in the wrong order. I just I didn't separate out the existence and the actually showing something. It's not exactly wrong, but it presupposed that the derivative existed. So first of all, we're to show that, we're to guess kind of a derivative for it. So we're going to guess that the derivative is t in this case, and so that would mean that we have that t of x plus v and is equal to t of x plus t of v plus this remainder term r of f. Sorry, r of x at t, and value to v. Okay, so we can actually just subtract this from this side, and then we get that r of x t of v is equal to 0 because t is linear. And now we want to show that this is bounded for all epsilon. For all epsilon, this is bounded above by epsilon absolute value of v. So the absolute value of this, of course, the absolute value of this is bounded by this. But this actually turns out to be pretty straight, like pretty easy. Like for all epsilon, like given epsilon greater than 0, choose. So if you remember your real analysis, you can choose your first real analysis course or something. You can choose any delta. Just choose delta equals 1, and then for absolute value of v less than delta, and you could choose anything because it's always 0. We have that absolute value of r of t of x at v is less than or equal to epsilon v, because this is positive, right? And because epsilon is positive and the modulus is positive, and this is equal to 0. And so for linear functions, we see that the derivative is like pretty straightforward to calculate. No, exactly. And there was like, and then we say that the derivative of t, and then afterwards, once we've shown that it's differentiable, then we call this the derivative. Is equal to t. Okay, so this is a very, very simple example, just because the people who made this definition up just wanted to work out like this. And so it's very straightforward. And this is the way you would go ahead and show that something is differentiable. And once you know it's differentiable, most of the time you pick some kind of derivative for it, and then once you know this r is bounded, then you know that's the derivative. So in the next video, I think the next thing to do is to show that if a function is differentiable, then it's continuous, right? So if a multivariable function is differentiable, then it's continuous. And that's what we'll prove next.